So meanwhile, Avery, you can prepare to the talk. Elias, you need to stop sharing, and then, okay, great.
How do I do that? Can you do that?
I took over.
Oh yeah, it's
great.
And let's wait half more minute before we start. Okay. Yeah, it's a good time.
Oh,
okay. Great. So the next talk is by Avery Miller from University of Manitoba, and this was the best paper in SPA 2018, and about labeling scheme from a radio broadcast. So Avery, you are welcome to start.
All right, thank you. So today I'll be talking about constant length labeling schemes for deterministic radio broadcast. And this is joint work with Faith Ellen, Barun Gorain, and Andrzej Peltz. And this appeared at SPA 2019. And I want to thank the organizers for inviting me to present at HALG. So just a quick overview about the model of radio networks that we'll be considering, and introducing the broadcast problem and motivating why we're thinking about labeling schemes. Then I'll talk about our results for broadcast and acknowledged broadcast, and then I'll talk a bit about future work and some of the partial progress that has already been made on some of the open problems. Okay, so first of all, here's a radio network. We're going to think about it as a graph. Each node in this graph is going to be equipped with an antenna that we're going to be using for wireless broadcasts. So I'm going to go through the model assumptions. So first of all, it's a synchronous model, so time is divided into slots. And basically what happens in each slot is that each node in our network has two choices about what it's going to do. Either it's going to set its antenna to receive mode, which means it's basically sitting and waiting, and it's capable of receiving a transmission during that slot. Or it's going to set its antenna to transmit mode, which means that it's going to be transmitting a message wirelessly during that slot. Some additional assumptions about how communication happens. So the first assumption is that a node cannot both send and receive a message in the same time slot because it has to choose which mode it's setting its antenna, either sending or receiving mode. The second assumption is that when a node is transmitting a message wirelessly, the signal from that transmission reaches all neighboring nodes in the network. And so what that means is that a node can't choose to just send a message to one of its neighbors, so it has to send to all of its neighbors at the same time, and it has to send the same message. It can't send different messages to different neighbors. So here's just a quick diagram. If we have our node here that knows some message M, and during the slot it transmits, then that message M will reach all of the neighbors in the network. Okay, so what makes this model more difficult to work in is the concept of interference. So if a message is transmitted, that message is not necessarily received by all of the neighbors due to possible signal interference. And so the third assumption we're going to make is that if two or more signals arrive at the same node P in the same time slot, then P does not receive any message. And this is called a transmission collision. So just to illustrate what's going on here, I'll give a few diagram examples. So in this case, we have two transmitting nodes, but they're very far apart. And so these green nodes each have exactly one transmitting neighbor. So they're going to be receiving a message from that neighbor. Here's another example where all of the nodes are deciding to transmit. And in this case, nobody receives anything because everyone is in send mode and they're not in receive mode. Finally, here's an example with a collision. So here we have this green node to the left. It receives a message because it has exactly one transmitting neighbor. However, this node red doesn't receive anything because it has two transmitting neighbors, and these signals interfere and cause a collision, so it receives nothing during this slot. Okay, one final assumption we have to talk about is whether nodes can detect whether a collision has happened or not. And so what we're going to assume is that there's no detection. So a node P cannot tell the difference between the following two cases. So the first case is that two or more neighbors have transmitted, so a collision has happened at node P, or no neighbors of P have transmitted. So essentially it's saying a node cannot detect between a collision and silence. All right, so that's a quick rundown of the model. With regards to the problem we're trying to solve, it's a relatively straightforward problem. What we have is a single node in our network that's called the source node. It has a message M. And to solve the broadcast problem, what we want is we want an algorithm so that eventually all nodes in the network know this message M. Okay, and what we mean by algorithms, so in network tasks, we're usually interested in distributed algorithms. And so what that means is that, the same algorithm is being executed by each node in the network independently of each other. And in each time slot, each node is going to be performing a step of the algorithm and making a decision if it will transmit or what it will transmit. And it has to base this decision based on what that node has received so far or what it has experienced so far, and that's called the node's history. And if the node has been assigned a label, then it can use that label also in its computation to make its decisions. And what we're going to assume in this work is that these algorithms being run by the nodes are deterministic, so nodes cannot flip any coins or make any random choices. All right, so let's think about a very simple scenario. Let's assume that we have this radio network with 4 nodes. None of the nodes have any labels, and we have this source node over here that has message M. And here's a very simple algorithm we could try to run at each node. So if I know the message M, I'm going to transmit it, and otherwise I'm just going to stay in receive mode, and hopefully I eventually receive M. And then so in every slot T, every node is going to be running this code. And so we can just watch what happens. In slot 1, the source node is the only one that transmits, and both of its neighbors receive the message M. Then in the next slot, all 3 of these nodes know M, so they're all going to try to transmit. Unfortunately, a collision happens at this rightmost node here, so it does not receive M. And in fact, this is what the diagram will look like for all time slots 2 and afterwards. So what we're going to notice is that this algorithm will fail. It will not solve the broadcasting task. Okay, and in fact, there's an indistinguishability argument to show that there's actually no distributed algorithm that will solve broadcast in this particular network, no matter how hard you try. And so why is that the case? Well, because there was too much symmetry. And the problem is that the 2 neighbors of the source node, they always have the exact same history. They will always behave the exact same way. Either they both stay silent or they both try to transmit. And in both of those situations, that rightmost node would never receive the source message M. But if the nodes have labels, for example, if they had distinct identifiers, then the nodes could use these in their algorithm to try to break this symmetry. And so this kind of inspires why we're thinking about labeling schemes. So if we look back to the vast majority of the literature that talks about broadcasting or various other algorithms in radio networks, especially in deterministic models, the model tends to assume that all nodes have already been assigned some distinct labels or distinct identifiers. And one advantage of having identifiers is that you can run a round-robin algorithm. So the nodes will just take turns transmitting. They just use their ID and they compare, their clock value to their ID value. And basically, this guarantees that each node transmits on its own, in its own slot, one at a time. So there's never any transmission collisions. And so you can perform really any task that you want because you never have to worry about collisions. And then so a lot more work has gone into making more efficient algorithms since round robin can be very inefficient. And so there's been a lot of work done on coming up with very efficient algorithms, but these are all or mostly done under the assumption that the nodes have been pre-assigned these distinct identifiers. And so what we wanted to do in this work is to consider a situation where the nodes don't have these pre-assigned identifiers, and it's actually our job to provide these labels to the nodes. And so a labeling scheme, lambda, is a function that's going to take as input the entire network G, and it's going to assign a binary string to each node in the network. And then our task is going to be to define such a labeling scheme that labels all the nodes in the network but also then define a distributed algorithm A that will solve broadcast when you execute it on the labeled network. And our goal is that we want to minimize the number of bits used in the longest label that the labeling scheme assigned, and this is called the length of the labeling scheme. And an equivalent way of thinking about this is we're trying to minimize the number of distinct labels used by the labeling scheme. And so this is sort of the scenario that we'll be considering for the rest of the talk, and that's considered in the paper. Okay, so first off, let's think about some simple bounds that we can come up with immediately. So one thing is that we're going to need at least 2 different labels. Any labeling scheme that can be used to solve broadcast, we're going to need at least 2 different labels. And we've actually already discussed this proof. Here's an example of a network where we're going to need at least 2 different labels, because the situation of all nodes having the same label is equivalent to the situation where all nodes have no label, or there are no labels at all at any of the nodes. So the same proof will work to show that there's no algorithm that can solve broadcast in this situation. All right, something not as easy is a relatively straightforward upper bound. So first of all, if we had distinct identifiers, we could solve broadcast as discussed earlier, because we could just run round robin and this would avoid all transmission collisions. So in this case, we would have log n bit labels in order to do this, but there's actually a more clever solution. If we think about or we let delta be the maximum degree taken over all nodes. And what we can observe is that there's a labeling scheme that uses big O of delta squared distinct labels and an algorithm that will solve broadcast in the labeled graph for using this labeling scheme. And so what we can conclude is that log delta bit labels will suffice. And this is not as straightforward to come up with, but perhaps a lot more obvious if I give you the following hint. What you can do is just take the graph and come up with a distance to coloring of the graph, and then you do round robin on the color classes, and this will also avoid all transmission collisions, and therefore it's relatively easy to solve broadcast. Okay, so those are 2 simple bounds. At least 2 different labels are needed. At most, big O of delta squared different labels are enough. What is the optimal answer? And so this was sort of the starting point of where we started our work. And it wasn't at all obvious. We tried lower bounds, we tried upper bounds. It took a while to make any progress. But what did we end up with? Well, we ended up showing that to solve broadcast, there exists a labeling scheme lambda and a distributed algorithm A, such that for any unlabeled graph with a designated source node and a source message M, our labeling scheme assigns 2 bits to every node. And when you execute the algorithm on that labeled graph, eventually all nodes know the source message. And in fact, this will happen within 2n minus 3 slots, where n is the number of nodes in the network. All right, so we had 2-bit labeling scheme for broadcast. We also considered a variant of the broadcast problem called acknowledge broadcast. And what we want is that eventually the source node finds out that the broadcast is finished. So then it can then perform any subsequent algorithms it wants, because it knows that the broadcast is over. So what we have is a labeling scheme lambda and a distributed algorithm. Once again, we have this labeling scheme. This time it assigns 3 bits to each node. And when you execute the algorithm A, eventually all nodes know the source message. This happens within 2n minus 3 slots. But then we also guarantee that the source node will receive an acknowledgement message at most n minus 2 slots later than that. So, and again, n is the number of nodes in the network. Okay, so that's a summary of the statements of the results. I'm just going to give you some intuition about how this works. So I'm just gonna give a relatively toy example, I suppose, or a straightforward example where we have this network that has 2 layers. In this case, it's bipartite. And all the nodes in the top layer already know the message M, and all nodes in the bottom layer still need to find out what M is. And so the main idea, or the first thing I need to introduce, is the concept of a dominating set. And this is going to be a subset of this top row, such that each node in the bottom row that doesn't know M yet is adjacent to at least one of the nodes in the dominating set. C, we're going to call it C. Okay, so here's an example of a dominating set. each node in the bottom row is adjacent to at least one of the orange nodes at the top. And what we're going to do is basically the nodes in the dominating set are enough. The nodes that aren't in the dominating set, we don't really need them in order to inform the bottom nodes. So what we're going to do is we're going to silence those nodes. We're going to assign them a bit or a label 0 to tell them, we don't need you, you can stay quiet. And then the nodes in the dominating set, we're going to give label 1, and that's going to tell those nodes, okay, when I see I have bit 1, that means I'm in the dominating set, I'm going to need to transmit. So then what happens is if we get all of the nodes in the dominating set to transmit, some new nodes on the bottom are going to receive M, but maybe some won't because collisions might occur. And so in this particular example I'm showing you, they all transmit on the top, and then the two nodes on either side here receive M because they have exactly one neighbor from the top row. But these two middle nodes have multiple neighbors in the top row, so collisions are going to happen, so they don't receive M yet. So we need to solve this problem somehow. And what we're going to do is, of the nodes that did receive M, we're going to want some of them to send back a response back up to the top row to tell some of these nodes to stay in the dominating set, and then everyone else is going to drop out. So the nodes that we want to send a response, we're going to label them with a 1, and everyone else we're going to label with a 0. So in this case, I'm going to label this leftmost node with a 1, and everyone else is going to be labeled with 0. And the way we chose is that we looked at which nodes on the bottom have not received M yet. Let's find a small dominating set that dominates just those two nodes in this example. And we're going to send a stay response to the nodes in this new dominating set. So in this case, what we notice is that this leftmost orange node here on its own will dominate these two remaining nodes at the bottom. And so all we need is that this node at the left sends a stay message up to this node, and everyone else can drop out. So that's what happens. The orange node that received the stay message stays in. We repeat the algorithm, so everyone in the dominating set transmits. Everyone on the bottom will now have the node message M, and we're done. Okay, so just a few remarks to make. This labeling function sort of does this simulation and goes through the simulation of how the broadcast will happen in order to decide which nodes to set to 0 or to 1, in the same manner as I just sort of ran through the simulation of what would happen on that network in the previous slide. And the example on the previous slide just took 2 iterations, but more complicated examples, this back and forth response might go on for a while. And each time the dominating set just gets smaller and smaller as nodes drop out. But of hopefully eventually, everyone receives the source message. So some immediate problems that might come to mind, because it's not obvious that this will always work. Certainly it worked in the example I showed you, but maybe in more complicated examples, some stuff might go wrong. So what could go wrong? Well, we sort of need a guarantee of progress. So if we think about all of the nodes in the dominating set at the top, in the top row, transmitting at the same time, how do we know that there will be at least one node that learns M? Maybe there's just collisions everywhere and no progress is made. And then we have a similar issue when we're talking about these stay responses that need to go from the bottom row to the top row. How do we know that those stay responses will be received? Because if there's multiple messages that need to go up, they might collide with each other. And so the nodes might not receive the stay messages that we want them to receive. And so this was sort of the main obstacle. And the main insight here is that as long as we choose the dominating set carefully, so as long as we choose the dominating set from the top row to be minimal, not necessarily minimum, but minimal, these two issues go away. And so obviously that requires some formal proof, which appears in the paper. But the idea is that if you have a minimal dominating set, you can guarantee this property that each node in the dominating set has something called a private neighbor. And this is a neighbor that's in the bottom row that no other node in the dominating set has as a neighbor. And so if you can kind of guarantee this private neighbor property, which minimality does, that's enough. That's basically the key insight to proving that these issues go away. Okay, so that's a description of the algorithm for the simple example of having a top row and a bottom row, and they're bipartite. First of all, we could quickly get rid of the assumption that this was a bipartite graph. What we noticed from our algorithm is that transmissions in the odd rounds were messages that needed to go from the top row to the bottom row. And in even numbered rounds, all the messages needed to go from the bottom row to the top row. So in fact, we don't care about any collisions that happen within the same row. We're not losing any important messages. So in fact, collisions within the same row don't matter. So we can add edges within the same row, never really affect the correctness of the algorithm. So that's one step towards generalizing this algorithm. With regards to generalizing further, I need a few more definitions. So I'm going to define what it means for a node to be informed, and that means it knows the source message M. A node is an uninformed node if it doesn't know the message M at the current time. And a frontier node is an uninformed node that has an informed neighbor. Okay, and this is basically all we need. And so basically, if we want to now generalize this algorithm to arbitrary graphs, it actually works in the exact same way as that two row, top row, bottom row example I just showed you, except now what we do is the top row is going to be the set of informed nodes. So no matter what arbitrary graph we're thinking about, if you just take the set of informed nodes and redraw the graph so that the informed nodes are in the top row, and then take all the frontier nodes in your graph and draw those as the bottom row, and then the rest of the nodes, you know, you can draw them wherever you want. But now you really just care about these two rows, the row of informed nodes and the row of frontier nodes. And then these are going to change as the algorithm happens, but you basically just run the algorithm as I showed you on the previous slides in that example. And then as the sets change, as nodes go from uninformed to informed, then you move them up to the top row and so on. And this is basically how the algorithm runs iteratively until all the nodes become informed. So it's a very rough sketch of how the proof actually works. It's just repeating this two-row idea. Okay. Now I want to talk a bit about how we perform the acknowledgement. So basically, we're just going to take the algorithm that I just described, just take the same 2-bit labeling scheme and the algorithm. And then what we're going to do is simulate the algorithm, this broadcast algorithm, and just watch what happens, and then look at the last slot where a node first becomes informed. And of those nodes that became informed in that slot, pick one of them, and we're going to call that node Z. And this is going to be the node that sort of initiates the acknowledgement process. And so now we're going to introduce a third bit to the labeling scheme. So Z's third bit, we're going to set to 1, and the third bit of all the other nodes, we're going to set to 0. All right. So now node Z, just by looking at its label, knows that, okay, I'm the initiator. I have to start the acknowledgement process. And the high-level idea is that there's going to be an ACK message that's going to be sent along a path starting from Z all the way back up to the source node. And so this Z node knows immediately what to do. So when it receives the source message for the first time, it sees in its label that its third bit is 1. So I know, okay, Z is going to immediately send an ACK message, and it's going to go to all of its neighbors. Now what we know is that Z at some point received the source message from some node Z1. And in fact, there's a unique neighbor of Z that informed Z because no collision happened. And so this neighbor of Z that informed Z is going to then send the ACK message after it receives it. And then we can continue this. There's a unique neighbor of Z1, which we call Z2, that is the node that originally informed Z1. And that Z2 is going to send an ACK message, and it propagates up and up all the way until the source node receives the ACK message. So this is sort of tracing the path of from Z all the way back up to the source node. And to implement this, we need to be a bit careful about how we do this. What we're going to do is alter the algorithm a bit so that every time you transmit the source message, you send a timestamp saying what the current round number is. And then when you're sending the acknowledgement messages later, what you do is you include the timestamp of the round when you originally received M. And then so anybody who receives this ACK message sees this round number and says, hey, I sent the source message in that round number. I must be the one who informed the node, so I'm going to be the one to propagate this ACK message again. And then this will just keep going up all the way till it gets to the source. So again, that's sort of a rough sketch about how this acknowledgement works. Again, full details are in the paper. Okay, so I quickly want to go over sort of what the open problems were and future work when I originally presented this work, and talk a bit about some of the partial results that have been solved so far. So what's left to do? Well, what we now know after this, after our results is that, well, we need at least 2 different labels. And we know for broadcast that 4 different labels are enough, and for acknowledged broadcast, 5 different labels are enough. But we still sort of have this gap between 1-bit labels and 2-bit labels. So the question is, what's optimal? And so are 1-bit labels always enough to perform broadcast, or are there examples of graphs where you're going to require 2-bit labels? And what we know is that 1-bit labels are enough for several graph classes. So immediately from this paper, it's not hard to see that if you have a bipartite graph, or if the distance from all nodes to the source is at most 2, you can get away with 1 label. It's just that, with 1 bit. It's just that that 1 bit is determined differently depending on whether you're in that top row or whether you're in that bottom row. But more recently, there's some work that came out earlier this year that introduced the level separable graphs, and they proved in this work that 1-bit labels were enough to perform broadcast in all of these graphs. And so this is definitely interesting. So basically saying that if you want to come up with a counterexample, you're going to need a pretty complex graph. And I sort of have a hazy intuition that 1-bit labels are enough to do it for all graphs. I don't really know how to formalize it yet, but I have a feeling it is. With regards to taking into account the efficiency of the broadcast algorithm that uses the labeling, so in what I presented today, the algorithms were linear in the number of nodes, so 2n minus 3. Can we get faster algorithms using constant length labels? And that was answered earlier this year at SPA. There are near optimal time complexity broadcast algorithms using 3-bit labels. And that was Faith and Seth earlier this year. But still, it's open whether you can get an optimal broadcast algorithm. And the optimal broadcast algorithm running time is d plus big O of log squared n. And if you just give all the nodes their schedule on when they should transmit and use that as their labels, then you can get the optimal running time with this length of label. But whether you can do it with constant length labels, still open. With regards to different models you can consider, well, you could consider different radio models. For example, if nodes could detect collisions. That hasn't been considered as far as I know. We can also think about the broadcast problem if the source node is not known when the labeling is being applied. And that's something that we extended in the full version of this paper, so you can check that out on arXiv. And then you could think about other problems other than broadcast. So very recently, I discovered a paper online where the authors consider the converge cast task. So they're talking about labeling schemes for deterministic converge cast. And I also have a recent paper with a student where we're considering multi-broadcast or gossiping. And once again, thinking about labeling schemes for that task. And still there's open questions involving these. And any other kind of communication task you want to think about in radio networks, I'm sure you could think about labeling schemes for those too. All right, so I'll stop it there. If you have any questions, I'm happy to take them.
Okay, thank you for this wonderful talk. Questions, you're welcome to write in the chat. So while people, there is a question. The ACK of Michael Rebbe, the ACK message, as its size, it grows up to log n. Did you consider the limit size of the ACK message?
No, that's very interesting. No, we did not think about message size at all. Yeah, that's certainly another dimension to think about. Yeah, because certainly you can do a lot when you can start encoding things in the messages, like timestamps or like histories or things like that. So you're sort of offloading some of the duties or some of the information that could, instead of putting them in the label, you could put them in the messages. So yeah, it'd be interesting to try to figure out if anything changes when you limit the size of the messages being sent. That's a good idea.
Mm-hmm. Okay, Liliana, is asking, is the number of ACK messages optimized? They add steps.
Yeah, I mean, I suppose yes in this case, because it's what's going to happen as soon as the last node finds out the source message, then the distance from that node to the source is the number of additional rounds used by the ACK messages, and you're not going to be able to get more efficient than that. At least that's my intuition.
Okay, more questions? So let me ask one question. Even if you have bipartite, the 2 layers case, how many times you may do this ping pong between the first to the second layer back and forth? I mean, it can be as large as n.
I think in that case, it's probably square root n. I think there's if I remember correctly, there's an example where it could be square root n. Is that right? Yeah, I remember we were thinking about this. So yeah, to my recollection, I think it could be as bad as square root n. Mm-hmm. Actually, going back to the ACK messages question, yeah, I just realized the path it takes back up to the source is actually the path that the source message took. It's not necessarily the shortest path. So yeah, it's possible there that there could be room for improvement about how much longer it takes to do the acknowledgement. But I'm not sure how you would do that. Yeah, it's a good question.
Okay, great. Thank you, Avery. And now we are ready for the last talk of Gopi. Okay.